Thank you. Good morning, everyone. So I'm going to present a joint work with Rafael, Bailon-Ruiz, and Simon Lacroix, which is about using a local search technique for observation planning with multiple UAVs. So this work was done in the context of the fire arrest project, whose objective is to provide fire responders with tools for automated monitoring of forest fires. And in particular, we're interested in the use of fixed-wing UAVs for this problem. So just to give you a few facts, so while wildfires typically occur in wildland and remote areas, which make the use of fixed-wing UAVs appealing for that because it's easy to deploy and they can reach distant targets. So forest fires are often concomitant. In risky areas, you can have up to tens of fire starts per day. They can cover very large spaces, so up to 1,000 square kilometers, but usually more in the size of 100 square kilometers. They are constantly moving, which is a speed of 1 to 10 kilometers per hour, and they highly depend on the environment, which would be the wind speed, the wind direction, the elevation data, and the fuel bed. So to give an idea of what we use as input of your problem before starting talking about planning or anything, so as input, we have an elevation map, a fuel map of the vegetation, essentially, a wind forecast, and we use this wind forecast to get, by simulation, the wind at the ground level, and we use this information then in a fire simulator that we developed to be able to predict the fire front's evolution over time. So in this example, you have a fire start here, and around you get the evolution of the fire front every 30 minutes. And so in this case, you have just a single ignition point, but you can also do that from an existing fire map and propagate it. And so we use this for as a prediction for the fire location over time. And so the planning problem that we want to solve is essentially to plan the observations on this expected fire front using a fleet of fixed-wing UAVs. And what we want to do is to maximize our ability to reconstruct a complete front from our observations. Now, this is not a simple problem because essentially there is lots of spatial and temporal correlations in the way fire propagates. And with this means that from a set of very sparse observation, you can reconstruct a mostly continuous front. And the consequence of that is that making an observation, if you've already made an observation, then making an observation very close to this one is actually not very useful because you could have inferred this information already from your previous observation. So essentially the utility of making observation depends on the other ones that you've already made. So if we want to cast this problem in a box, essentially I would say it's an orienteering problem for operation research where your objective is to, where you have a set of checkpoints and you want to, each one has a score and you want to visit as many checkpoints as possible in a time budget, and you want to maximize the score that you collect. So it's very close to this orienteering problem, but we have lots of additions. So essentially you have a very large and continuous search space. You have multiple agents and they all have kinematic constraints because fixed-wing UAVs move very fast and they cannot turn in place. You have time windows because the fire is constantly moving, so the fact that you can make an observation depends on the time at which you arrive at a given point, and you have non-linear objective functions. So the way we model, so we wanted to model and solve this problem in an efficient and hopefully quite generic way. So the first thing we do is we have a motion model that is quite simple and essentially a black box where we have a waypoint, whatever it is, and we have a travel time from one waypoint to another. We also have energy consumption, like that, but I'm not going to talk about this in this talk. So what we use behind the scene for this black box model is actually Dobbin's path. So you have 2D coordinates and an attitude and orientation of your UAV, and you can get the travel time of this between 2 points by using the shortest Dobbin's path. So it's the bin space is actually constrained by your maximum turn radius. So this is a quite simple but hopefully quite realistic representation of this. So then the next building block is maneuvers. So we define a maneuver just as an entry point, an exit point, and a duration. So typical examples are straight lines. That's actually the one that we use because it means that your UAV is going to be in a stable position when you can take a picture before going on with the rest of the trajectory. So we use very short straight lines, but you can also use things like lone mouners and embed this into this definition of a maneuver. Then a trajectory is just a start time and a sequence of maneuvers. And then from your motion model, you can go back. You can compute all the intermediate times of your maneuvers. And then a plan is just mapping from each UAV to a trajectory. And you can have validity constraints such as the maximum flight duration and starting positions. And then you have an objective function. It's just utility of your plan. And we don't need to know more than that. But for the fire monitoring, essentially, we have mapping from maneuvers to observations, where a maneuver is an observation if it allows you to take a picture of the fire front. So essentially, it puts spatial and temporal constraints with temporal and spatial conditions for this transformation. And then the utility is a sum of the knowledge that you get from your observations, and this knowledge actually depends on distance to other observations. So now, for planning, we use a local search technique, which is variable neighborhood search. So a neighborhood is essentially just a mapping from one plan to a set of neighbor plans that you typically get by applying simple transformation. We extend that with the local utility function. That is a local view of the utility from the point of view that is neighborhood. So that can be the global utility 1 or just the total duration of your pass and things like that. And then a generate neighbor function generates from an existing plan either a new plan that improves your local utility function or fails. And the way you generate that is by either exhaustively or by sampling your neighbor space and then trying to see if you can find one that actually improves your utility function. And so then we build different neighborhoods and we essentially try to decouple the different parts of building and optimizing a plan. So the first one that we use is for pass construction. So it's a two-step process. So in the first part, we sample an observation that we can make. And then we select an insertion point in your plan, and that just defines a new plan. So the way we generate neighbors is by sampling. So we sample a set of observation, a fixed number of observation, and we select insertion point for those. So there's different heuristics you can use for those, and I'm not going to present them. And you select the one that gives you the best global utility, and you tie break for duration. So if you apply this on this very small fire, you would get an initial one that will give you your first plan. So you actually get from your start and end point. So it's already a round trip, and now you have one observation in your plan, and you can transform this again with the same neighborhood and add new observations. So you don't have to add observation at the end. You can add it at the beginning or in the middle. It actually does not matter. So that's how we construct paths from an initially empty one. And then we have another neighborhood which is for path optimization. And the idea is also very simple. You select an existing maneuver in your plan and you apply a simple transformation to it. Typically a rotation works really well in your setting. And then you have your gen neighbor function for which you also sample your neighbor space and you select the first one and improve the duration. So if we want a simple example, imagine we have a new insertion in this plan, and this actually results in something that is quite weird there, because you have, due to the fact that you use Dobbin's path, you have a path that is weird looking and clearly suboptimal, and this neighborhoods will essentially try to many different local adjustments, and hopefully you will get something like this by simply rotating around things. And you have a last neighborhood, which this one is actually domain dependent. And the key idea behind this neighborhood is when you insert maneuvers at the beginning of your plan, it delays all the other ones. And because our observations have time windows associated to it, because the fire is always moving, it means you can miss observation because you insert maneuvers at the beginning of your plan. And so this one, what it does, it exploits the structure of the fire map to move maneuvers onto the fire front, or remove it if the maneuver is actually too far away from the fire front. And so then the way we combine these into a viable neighborhood search is quite simple. So essentially you have a sequence of neighborhood, which in this case is our the three neighborhoods we just saw, so project and fire front, optimize path, and insert maneuver. And you start from an empty plan. And then you try to improve it continuously. So we apply the first neighborhood, and if this provides an improvement, you will start again from this neighborhood. You will do it again. And once it fails to provide an improvement, you go to the second one. And once again, if this provides an improvement in your plan, you will again go back to your first neighborhood, try to improve it from there, and then keep going. And once you reach your last neighborhood, well, if you have an improvement, you go back to the first one, and if you're not, then it means you've reached a local minima, or you're likely to have reached a local minima, because we use sampling, so we have no guarantee of being in an actual optimum. But what you try to do next is to escape this, and so you have a shuffling function. So there's also lots of ways to define shuffling function, and one option is to just remove sequences of maneuvers from your plan, and this gives you a plan that is full of holes, and you can start optimizing again by going back to the start and doing your descent phase by applying all your different neighborhoods in sequence again. So to give you some idea of how this performs, so we did some tests on areas of 10 by 7 kilometers where we simulated 1 to 3 fires. So on average, this gives us a bit more than 2,000 possible observations. So we actually have a fixed number because the fire map is discretized to allow the propagation to occur. But each of those observations can be made on any angle. We don't make any assumption on this. And so we have 1 to 3 UAVs with an airspeed of 64 kilometers per hour, and that have flight windows of 10 to 30 minutes. And so that's the kind of plan that you would get. So here you have 3 fire sites, this one, and the 2 there that got merged. And you have 3 UAVs. So the first one to act is the green one, that starts from this corner and maps this fire front very early on while the fire is still very, very contained. And then you have 2 other UAV, the red one there, that arrives much later and will map this part of the fire. It actually does not map this part, which is the least active, and therefore not very interesting from the objective function point of view. And then this UAV goes on this part and maps this part of the fire front, and the blue UAV will essentially map the other part. And that's another plan where you also have 2 UAV that share the task of monitoring 2 fire fronts. Essentially, the red one does the lower part, and the blue one does the upper part. So some insights. So essentially, we're able to compute reasonable plans in a matter of milliseconds. The 2 plans there where I stopped the resolution after 20 milliseconds to get them. And the algorithm usually converges in 10 seconds, and after 10 seconds you will get plans that are much denser than those examples, and also much harder to read, and that's why I did not show them here. We make only very minimal assumptions on the Marshall model and the objective function. And but still we're able to plan with very fine-grained primitives, and that's something that we really wanted to use. And if you look at the literature, usually you get you're only able to plan for large maneuvers, like you will consider 4 lone mouners and things like that. And this is not applicable in this case because essentially you're trying to observe lines that are moving, and so covering surface areas is not possible. And so the coordination is entirely derived from the objective function, and we did not have to add anything specific in the planner to do that. One of the frustrations that we had is that we have actually no baseline to compare with. Essentially, we did not find any approach that was able to handle this problem without drastically reducing it by making the objective function linear, by removing the time windows on taking only one agent and removing the dynamics of the model. And so you would have to remove at least 2 of those to get another approach to solve those. So we have no baseline comparison, which was really frustrating. There's lots of comparison against ourselves in the paper if you want. I have some in the backup slides if you want to talk about it, but I'm not going to present them. So as a summary, it's an embarrassingly simple solution to a complex problem. Everything in this algorithm is simple, and it's just a combination that gives you really good results. We do make only minimal assumptions, and the great thing about this approach is that it's actually very easily extensible. And here a good part of the performance comes from just adding one domain-specific neighborhood in the local search process. And so since the paper, there's been quite some extension, mainly on modeling. So we've added motion models for elevation, to take into account elevation, to take into account wind, for enhance the utility functions. It's been integrated with a simulator, and there's some real tests that are planned for this summer, I think. And we also do online plan adaptation, so we constantly feed the algorithm with new outputs with the new fire map. And essentially the planner now acts just as a complex heuristic to just check the next what is the next maneuver to do, but it's always you to take to have a long-term view of what you're doing. And thank you. So if you have any questions.
Okay, got it. I have 2 questions. I quite miss why the current existing solution to the dynamic multi-vehicle routing problem for Dobbin's vehicle cannot...
Question?
I mean, why you cannot use the existing solution to the problem of multi-vehicle routing problem with Dubin's constraint? So, and so my second question is, how do you handle UAVs in intersection while they are moving? So collision avoidance of dynamic UAVs. So that's my 2 questions.
Okay, so for multi-vehicle routing, essentially in this case we don't have to visit all the possible points that we know.
That's the whole point of dynamic multi-vehicle routing. They don't have the whole points in advance.
Okay, then it's probably the orienteering problem that a different name for it. Essentially, if we go back to the slide, where is it? So you have solutions for the orienteering problem. You have some solutions for the orienteering with multiple agents. You have some solutions for orienteering problem with time windows. You have some, not very satisfiable solutions for orienteering problem with nonlinear objective functions. There's some for vehicle routing with dynamic constraints, but there's really nothing that takes into account, I think, more than two of these. So we really add nothing to, definitely our approaches take into account what has been done for the orienteering problem in our extensions of this, but we could not use any other.
Hi. So I came in a little bit late. Maybe you've already answered this in your earlier slides. As I understand that you're trying to observe a fire front, is that right? Using multiple UAVs. But what I was wondering about is during a fire, there's often smoke.
Yes.
A lot of smoke. And I guess that can impede your ability to observe the front directly. Do you account for that? Have you thought about this?
Yes. So the first thing to do is to use thermal cameras because, yes, there's smoke. And from what we've seen and discussed about this with actual professionals, it's not that big of a problem, which was really a surprise from my point of view. I was expecting to really have to take this into account while planning, but apparently it's an assumption that we can make that there's no smoke, which I'm not very happy about, because it feels really not natural to me. But apparently you can do this. And so we essentially use thermal cameras to be able to see through the smoke, but except for that, yeah.
Thank you.
I guess in your problem, you assume that wind exists. So because the wildfire, it moves with wind. But how do you, how do you take into account wind in the kinematics of your UAV?
Okay. So in the paper, we do not take it into account because the Dubbin's pass does not take that into account naturally. And since then, we've used Dubbin's pass with wind. So essentially, it means that you try to find a Dubbin's pass to a moving target, where your target is moving due to the wind, and so you have a very short and simple to solve optimization problem to actually find your shortest path to take wind into account. But you can definitely use that in your kinematic model.
Okay. Yeah.
Hi. Yeah, it's a great application of AI. And are you considering using something different than Dubbin's paths? Because Dubbin's paths are kinematically feasible, but if you consider dynamics, it's infeasible because you have the curvature of the path is changing abruptly at segments of Dubbin's path. Are you doing a kind of smoothing, or is it just a problem of your controller?
Yes. So Dubbin's paths are, in my view, a very good approximation of the thing you can do, and this is very useful to plan. And as I said, we actually discard most of the plan because we aren't really, in the end, only interested in the next few moves. But one thing we're looking into is actually the limitations of the controller of the UAVs mean that we cannot target an orientation, which means using Dubbin's is limiting on this particular controller for the UAV. And so one thing, not me, but another person was looking into, is to use directly a simplified model of the controller to essentially simulate what giving particular targets to the controller would do. And one of the difficulties of that is that you have to simulate everything because since the controller only accepts waypoints without orientation, inserting something in the beginning might change the orientation in all the following ones. So there's definitely a computational cost in doing this. But you can probably find some approximations.
Okay, thank you.